Okay, let's get started on this wet Monday. Okay. So now we're going to be looking at the tight binding model, and this is coming at it from a kind of different way to the free electron model that we have looked at, the nearly free electron model that we looked at last week. So in this approach, we consider electrons as they are in their atomic configuration. For example, you've got there a sodium atom, and you can see its various electronic orbitals. You have the most tightly bound 1s electrons, then the 2s electrons, 2p electrons, and the most weakly bound 3s electron. And this is the way we write the electronic configuration. Here you have the orbital, and the superscript there indicates how many electrons you've got in that orbital. So you can see the S has got 2, and the P's got 6, and the very outer one has only got 1 electron, and it needs another electron, so it actually readily gives up that 1 electron. So in this approximation, or this model, we assume that the electrons are sufficiently tightly bound to their atoms so that they are identified with the quantum states of the free atom, and then what we're going to do is bring those atoms together and see how those levels are changed. I think early on we sort of had a little idea about what's going to happen here. This here on the left-hand side is for a free atom. You have your various quantum levels here, n equals 1. That's the most tightly bound s electron. Up here you have the 2s electron, and there you have the p states. So this is for a single atom. They're non-degenerate electronic levels here. Now, when you start bringing lots of those single atoms together, over here, if they're far apart, we still have the discrete levels. But of course, instead of just 1, they are now degenerate because you've got n atoms. Now, as you go along this axis here, what is happening is you are bringing the atoms closer together. So you can see the broadening of the energy levels and the interaction of the electronic orbitals on each atom with the other atom here. Okay, I think plotted as the inverse of the atomic spacing. So here your atomic spacing is getting smaller and smaller. Okay, so that's how you can view the energy levels as changing as you bring your atoms together. If you want to look at how the wave functions are on, for example, 2 atoms, this represents the position of 2 sodium atoms, the red dots, and they are spaced about 3.7 angstrom apart. I'm actually not sure if that's the equilibrium lattice constant of those 2 sodium atoms, but it's quite close together where you might get some bonding, and this just shows what the various wave functions look like. Okay, so the most tightly bound 1s electron, as you may expect, is the most peaked one. It's very localized to its atom. The 2s is a little bit more extended in space, still doesn't overlap very much with each other. The 3s here is the most widely extended, spatially extended state, and you can see that there's quite a lot of overlap of the 3s electron from the 3s orbital of this atom and this atom. You can see that by the electron density there between the atoms. So that's a nice way of, you can also imagine how those orbitals look on your atoms. Okay, so now we have to sort of think about modeling this kind of situation. And so what we're going to do here is assume just a one dimension for a start, So these represent your atoms, and we are going to consider just a single orbital on each atom N, represented by these numbers here. Okay, we have that those orbitals are orthogonal, as usually the case, and we are going to take a trial wave function of this form here, where we're going to expand the wave function in terms of a summation of the orbitals of all of those N atoms. And the corresponding Schrödinger equation can be written here. Here's your Hamiltonian, and these are your these are the orbitals of the atoms here, and your energy eigenvalue. And yeah, put here Ashcroft and Merman, chapter 10, has all of this in a lot of detail, but probably more detail than you will need to know. Okay, so what's happening here? So we're going to be writing the Hamiltonian as the kinetic energy term represented by K, and we know that that's equal to P squared momentum on 2m. And the V here is some kind of Coulomb interaction between the electrons on the atoms. So basically, we're just going to substitute this expression, K plus the sum over the potential, in for our Hamiltonian, and write it like this. And what we recognize is the first term here is just that corresponding to a single nucleus or single atom. So this term here is just for one atom, doesn't feel the other atoms. Okay? This here describes the interaction on one atom with the atoms here. So this here, we can just write it as the energy levels of that atom. Okay? So the energy here is just those. Remember we had that potential well, and we had the various eigenenergies? That's what these E atomic represent, just those levels from the single atom. So that's the first step. And what we're going to derive, I'll just show that quickly, what we're going to get to, we have a bit more work to do, sorry. Okay, so where's my stick? And we'll go through it a little bit together. So now we have rewritten this first term in terms of the atomic orbital, energy orbitals of the single isolated atom. And we're going to deal with this term here now, okay? So you can see that this involves a summation over all of the atoms, right? But what we're going to do is limit that to just the neighboring atoms of that one. If you consider one atom here, we're only going to consider the nearest neighbor atoms, okay? It's a little bit of a drastic approximation, but this is what we are doing here because we're assuming it's a tight binding and it doesn't really extend too far out to interact with the other atoms. So that's what we're doing here. So N and M need to be very close in energy. So if we are an atom N, we are going to consider just the interaction with ourselves, which is obviously just V0. And then we're going to consider our neighbors, M plus 1 over here and M minus 1. And everything else is going to go to 0 otherwise. So basically, we end up with this expression here. We're going to just derive that together in the next page, I think. This T here is an energy term, and it's commonly known as the hopping term. Okay? So it tells you how likely and how easily can an electron that's located on one atom hop or move to a neighboring atom. If T is big, it means it's easy to hop to a neighboring atom. And if T is small, it means it's not easy to hop to a neighboring atom. What determines whether it's easy or not to hop to a neighbouring atom is, for example, how close the energy levels are between the atoms. If the energy levels are close, then it takes little energy to hop to the other atom, and that's when you'll get a big T. If the energy levels are widely separated, it costs a lot of energy to hop, and you'll get a small T. Okay. So let us, as I say, get our hands dirty. And I never know which one to put this on, and it's always the wrong one. Okay. Okay, so let's just go through a little bit of that together. We have our Schrödinger equation for this situation. Sum over the atoms M in our system, Hamiltonian, trial wave function. Remember, our psi was going to be a summation over these kind of orbitals of each of the atoms, energy eigenvalue psi of n. And we're going to try solutions. These phi are going to have the form normalized, and then just e to the minus I k n a. Call this 1, call this 2. So very simple kind of wave functions. And we had from before HNM was equal to the isolated atom energy levels Nm, so it will be 1 when we are actually on that atom and 0 otherwise, minus T delta N plus 1 M. We're only considering, this term considers our neighbour, say, to our left, and we are only going to consider the other interaction with our neighbour to the right. So if we substitute 2 into 1, so we're just going to substitute these wave functions into our expression there. And if we just look at the left-hand side of equation 1, which is first of all the Hamiltonian part, then we will get sum over M, N, M, phi of M, sum over M, E0 N M, delta N plus 1 M plus delta N minus 1 M, all multiplied by our phi here, e to the minus I k m a, normalized. Okay, so, you know, that's fairly straightforward, and we could have seen that anyway. But we're going to sum over M equals to N, M equals to N minus 1, and M equals to N plus 1 only. So this will get us, for firstly M equal to N, E0 delta N N, obviously that will be 1, and so you have to put that in like all the way along, M plus 1 N plus, hang on, yeah, and N minus 1 N, and then your wave function here. And so obviously this will give you 1. These will cancel out, okay? So you kind of get the idea now. And then we have to add to that the next summation, M equals N minus 1, for example. Then we have E0 delta N, N minus 1, minus T n plus 1, n minus 1, plus delta n minus 1, n minus 1. And then just this wave function again. So when you look at it in this case, these delta function will go out because they are not the same, and this one will go out because these are not the same, and we will just be left with this term here. So we get this term from this term from this, and you can probably guess why we now get the third term. So now m equals n plus 1, so we get delta n plus 1 minus t delta n plus 1 n plus 1. Okay, now I think it becomes quite clear what's gone on. So in this case, this will go out, and this will go out, and we'll get that. So then we can easily now gather up our terms. E to minus I k n a minus t e to the minus I k n minus 1 a over square root of n plus e to the minus I k n plus 1 a over square root of n. Okay, so we have that. Remember, that was the left-hand side, and the right-hand side was just, right-hand side of equation 1 was just the energy eigenvalue, psi of n. So e to minus I k n a over square root of n. We're not quite finished yet. Obviously, we're going to equate those two expressions. So you can expect what's going to fall out is these n's can disappear. And what we're going to do is just put this term on the right-hand side. Okay, get rid of, put this over there, and just work out these exponential parts here. And when you do that, you end up with E0 minus t e to the I k a plus e to the minus I k a. And when you work these things out, you know, cos ka plus I sine ka, the sine parts will cancel out, and you'll end up with E0 t2 cos ka. Okay, so that's what has been done in order to get that expression that we had. I want to go just a tiny bit further now because it's on the slide, but it helps if we can perhaps look at it while we have that expression here. So we want to now plot this function here, sorry, this one here, the energy as a function of k there. So if we consider at k vector equals 0, we just get that the energy is equal to E0 minus 2t. Put that equal to 0, the cos term will just go to 1. Okay? And then what you can do is take the E0 on the same side as the energy, and you get minus 2t. And this is what's been done like in the lecture notes that you may have already seen, or if you haven't, you'll see right now. So if we plot on the y-axis E minus E0, so we're calling this the y, then at k equals 0, we have a value of minus 2t. Okay? And then we can consider another point at k equals pi on a at the Brillouin zone boundary. So at k equals pi over a, we get E minus E0 equals minus T2 cos of pi on A times A. Okay, these obviously cancel out. And cos of pi gets you a -1. So we will just get minus T2 times -1. That will get you plus 2t. Okay, so at k equals pi on 2, we get a value of plus 2t. So basically the plot looks like that, the dispersion curve for this kind of tight binding system that we have, one-dimensional system. Okay. So let's go back now to our overhead. And I think we're on the next page now. Yeah, so this is what we did together, basically. We, derived down to this, and then we saw how we obtained this curve here. Okay, so this was your minus 2t, this was your plus 2t. Actually, it's in units of t as well, so this is plus 2 and minus 2. And this distance is 4t, and this is called the bandwidth, okay? From the top of a band down to its minimum, it's called the bandwidth, and in this case, it has a bandwidth of 4t. And remember we said that t was this hopping energy, so that you can see if you have a small hopping energy where it's difficult for electrons to hop from one side to the other, you will have here also a small bandwidth, okay? When you have a large t, a large hopping, you will have a larger bandwidth because t is bigger, and this interacts a greater interaction of the orbitals if the bandwidth is big. I skipped over that, but now I think it's better that I show it here. This is basically exactly what we have derived, but it's plotted as a function of interatomic spacing. For example, the result that we had, we were working at a particular lattice constant, and we may have got our bandwidth, say, at this width here. That may have been our 4t. But if you reduce the distance between the atoms, you'll get a greater interaction of the orbitals, a larger value of the hopping energy as you squish them together. And as you would expect, as you increase the spacing between the atoms, you have a smaller bandwidth and a smaller t, and in the extreme you go back to your isolated atom energies. Okay, what else do we have to do now? Okay, so we have got our equation, a dispersion curve if you like, energy as a function of k, equation here for the tight binding one-dimensional system. And we're only going to do one-dimensional system here, but it can be extended to the 3 dimensions quite straightforwardly, but we don't need to do that. So what's the point? The point, we are going to try and determine the effective mass for this particular tight binding model. So what one can recognize, if we go down to the bottom of the band, we can see that it's very similar to our nearly free electron kind of parabolic shape. So if we expand this equation for our curve, for small k near the bottom of this curve, then we can get this expression here. This can be approximated to this expression. Okay. Why and how? It's just because of this here. Use this approximation, okay? For small angle, we can approximate cos of theta equals to this expression here. So then you can just substitute it in and expand it out, and you can recognize that this first term is just a constant. That's just our hopping energy. That's our energy of the isolated atom. And so this is the way they've ended up with this expression here. So what's the point of that? The point of that is that we can recognize that it is sort of a parabolic shape. Energy goes as k squared. And then we can determine our effective mass by comparison to our free electron case here. Okay, so we had this expression from our, I think, our nearly free electron model, this kind of behavior of the dispersion curve. And if we equate that to what we have just determined there for this parabolic part, then we can derive an effective mass for our tight binding Hamiltonian. So it's equal to h bar squared over 2t a squared, just from this expression here. Fine, good. Okay, changing, we've derived that, that's the main thing. Just some other interesting things here. Coming back, I think we did that a bit Friday? Yeah, Friday. We talked about band filling and so on. So remember that we had, if we have an atom that's just got one valence electron and one band, we get a band that is completely half filled because there are n k vectors that are allowed for this whole band. It can occupy 2n electrons, and if we've only got one electron per cell, we only need to occupy n states, so we only fill it half full. Now, if we apply an electric field to a solid that has this kind of band, what happens is we get a slight, these electrons experience a force, and it causes them to shift to the right here. So the bands just above the Fermi level become populated, and the electrons on this side of the band become slightly depopulated. So that's what happens if you have that kind of band and you subject it to a small electric field. And on Friday, we saw the situation where we had 2 electrons per atom with just one band, and we know that in that case, the band is exactly completely filled. And in that situation, if you apply a small electric field, then nothing will happen. There will be no current that can flow because the bands are completely filled to the top, and they have nowhere to go, no states to jump up into. This is kind of illustrated here. Again, basically what I just said here, this is a situation where we have an applied electric field. This shows the direction of the electric field, and the electrons will move opposite to the electric field. So that's why this side of the band becomes populated. In this situation, as I said before, we have a filled band, completely filled band, and in an electric field nothing is going to happen. There is no states for it to move into. And this is, you know, the situation you have if you have an insulator. Okay. Okay, this is just a little kind of animation to show that when you do apply the electric field, the electrons move in the direction opposite to the electric field. Okay, so the electrons go to here. And what happens is when they get to the Brillouin zone boundary, they get scattered and they go back to the negative pi on A. So this is called block oscillations. We're not going to go any more deeply into that than just to let you know the name. So in an electric field, you can get this oscillation of these electrons back and forth in the Brillouin zone.
Sorry, Kathy, are these slides on this?
Sorry?
Are these slides on this?
They will be. These are extra ones I put in. Yeah. Okay, I think, okay. This is just a little bit more of the same. Remember from last Friday, if we have 2 electrons per cell and 2 orbitals, only one orbital will be fully occupied because both of those electrons can go into that state, and the other will be unoccupied. But this just shows how a metal insulator transition can occur. For example, the equilibrium lattice constant might be here, for example, and you've got a semiconductor. Say the bottom band might be completely filled and the top band might be completely empty, so it's a semiconductor. But if the atoms are made to move closer together, then as we saw, the bands become broader, and at this point it becomes a metal. Okay? So there are some materials where you can induce either a metal to semiconductor transition or an semiconductor or insulating transition into a metal just by changing the lattice constant through strain or epitaxial growth or whatever mechanism. I think we kind of went over this with the nearly free electron model very much on Friday. The same thing for the tight binding model. Just talking about which bands will be completely occupied or not. Let's just have a quick look here. If we have 2 atoms per cell, each with 1 orbital, then you're going to get 2 possible bands. Okay? Each band can occupy 2 electrons. So if you have an atom that has 1 electron, monovalent, then only the bottom band will be completely filled. Both electrons can sit in there, okay? Even if it's got 2 orbitals. If you have a divalent atom, 2 electrons on each atom, then you'll have completely filled bands. Okay? And as we saw from the example of beryllium, we saw that we had the possibility to have a completely filled band and the possibility to have an insulator or a semiconductor. But remember, it was metallic, and that kind of situation can happen if your bands, if they don't look like that. In that case, you have your 2 electrons occupying the bottom band. That one's completely empty. But what if the other band dips below the top of this band? And this situation can also occur in materials. And in this case, rather than having like a band gap, having a semiconductor or an insulator kind of structure, you'll get a metal, because the Fermi level here has cut completely the band, and the electrons can easily, with a bit of thermal energy, they can easily jump up into the unoccupied state. So this is metallic, okay? So, yeah, the details of the band structure depends, very much on the kind of material and the kind of structure that you have. It's not always this kind of idealized situation. Okay, so we looked at one dimension. You can also plot in 2 dimensions if you want. So what does this show? This is the square illustrates your square Brillouin zone of a cubic crystal lattice. You're looking down on it, for example, or you might just have a 2-dimensional system. In the free electron system, you'll have just a perfect sphere like we saw very often, right? And when we have introduced some kind of potential, either through the nearly free electron model or even the tight binding, you will get gaps opening at the zone boundary, so it can have a kind of unusual shape. It does not have to be spherical or circular. And for example, this shows the Fermi surface for copper. So you can see it's very much kind of spherical, but it has these kind of necks that reflect that it is not a perfectly free electron-like kind of material. And a lot of people, experimentalists, spend a lot of energy and time mapping out the Fermi surface of complicated materials, usually using angle-resolved photoemission. Okay, now if you have 2 electrons in your system, and we just have the one band, then your band is going to be filled to the brim, basically. So here your Brillouin zone will be completely filled in comparison to this situation where your band is only half filled. So the filling of the complete Brillouin zone reflects that your bands are filled up to the complete edges of the Brillouin zone. And if you have intermediate strength, you can have these kind of unusual Fermi surfaces in 2D. This is a picture of the tight binding model. As you can see, basically it's basically this structure here. Okay, it's just this one again, but it's been calculated, and in 2 dimensions you can recognize this kind of equation, but now we've got x and y. So this again is for a single atomic orbital with 1 electron on a square lattice. So this is empty, empty, empty. And if you, like we have been just making a 1-dimensional cut through here, that would be, if you look at it, the energy of it, that would be your band at the go down, and up here, band gap at the Brillouin zone boundary. Okay? So we have normally been making just a cut through the center of it. Okay? Okay, changing topic, not really, but just defining, what we mean by direct and indirect transitions. Does people know about this kind of? Anyway, it's quite straightforward. If you're having a system that's, say, excited by radiation, you might get a transition from an electron here in the valence band straight up here to the conduction band. If the transition is vertical, we call it a direct transition. It can also happen that you get a transition from here at the gamma point in the middle over to some other part in your reciprocal space, okay, over to this part here, which is called an indirect transition. Okay? And this would be called an indirect semiconductor. A direct semiconductor is where the band gap is between the states that have the same K vector. So this would be a direct semiconductor if this thing was not hanging down here, if this was up higher. But because this is the lowest conduction band, and it's not at the same K point as the valence band, we also call that an indirect semiconductor. We're going to get to semiconductors later, but before that we have to do phonons. Okay? This is important, this is interesting. Okay, so we've got here our schematic band structures, our dispersion curves, our energy versus K plots, okay? This is the band structure. In this case, there's a band gap. It's a semiconductor or an insulator. Over here, no band gap. It's a metal. What you can do is plot the corresponding density of states. Okay, remember the density of states we talked about right at the start? That is how many electrons we have as a function of their energy. Now, these have a one-to-one relationship, okay? And people very often in their research plot out both of these properties, and we're just going to look and see how they are related to each other. Okay? So this plot here corresponds to this situation. This is energy here. This is energy here. Okay? So for low energies, we have a certain density of states. Bit higher energies, we have another bit higher density of states, and at a certain energy, valence band maximum, we call this, there is no density of states. Okay, this corresponds to this. Okay, down here, we are down here. We go up a bit higher, we come to a band gap. We are here. Okay, then we cross the band gap, and we have the conduction bands here. Here, the conduction bands here. Same thing over here. We have, the low energy bands have a certain number of them, G. We are down here, okay? And then this part, you can see this little dip in here. That corresponds to this little dip here. Okay? This shows you, that was more of a toy model, what I just showed you. This represents like the real band structure of silicon. And, normally we have just considered sort of these kind of bands, this parabolic part, and maybe another band up here. But we know that in the whole Brillouin zone, we can plot out other directions in K-space, okay, like we saw from our three-dimensional Brillouin zone, BCC or FCC. These are specific points, and these corresponds to specific lines in K-space. And along here is plotted the density of states. Okay, it's not plotted, it's being turned upright so that you can exactly see that they correspond to each other. We have to keep in mind that we have, in this band structure, it's only a plot along lines in particular direction. There will be lines in all directions in K-space, okay? So the green here corresponds to just the green bands, okay? The red corresponds to just the red bands. And the red bands are identified with the S orbitals. So you can see these are S kind of orbitals. And the green is P. And also plotted is the total. So from integrating over all of the Brillouin zone, you get the whole grey. Although you can see the red and the green, they do reflect the character of the total density of states. What's the point? The point is, how do we understand the relationship? Well, this equation here. Okay? This is derived in Ashcroft and Merman, but you don't need to know the derivation, and I'm not going to go through it. But what's the main thing to take away is that the density of states, G, along this axis here, is inversely proportional to the gradient of the E versus K band structure. Okay? So let's take a look here. The gradient along here is low. It's small. Rise over run. It's kind of flat. It's small. So the density of states should be large. And that's why we get this big peak here. Okay? Conversely, the gradient is quite high here for this part, and the density of states are low in that area. Okay, it's fine to have that relationship, and we can see that it correlates, but we can also understand that by knowing that this is the number of states per energy level. Okay, remember that there's only discrete values of K that are allowed in the band structure. So K is equal to 2 pi and L, remember? Here, 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 here. It's uniformly spaced. And you can see that for this small energy interval, you have very many dots, very many K points. Okay? Whereas down here, they're more in the Y direction, they are further spaced apart, so you have a smaller concentration of the density of states. Okay? This is really nice. It's really also kind of fundamental. So try and get your mind to remember that. Yeah, this is just a little bit more, making sure you understand the difference between metals and semiconductors. Okay, remember this from the very first lecture or so. This is your density of states just for an ideal situation. This here shows you some density of states for a typical, this is a band gap, okay? Forbidden gap, no electrons can go in there. So if you have a metal, you can fill them up, the bands up to a certain point, and there is a finite density of states at the Fermi level. Okay, so that's one way of remembering this is a metal. Semiconductor, the band is completely filled. At the Fermi level, there is a zero density of states. Okay. I think that's basically just what I said there. Yeah, it's important to realize too that certain elements can have band gaps in certain parts of their electronic structure, but to be a semiconductor or an insulator, it has to have a complete band gap all the way through your material. So if you put the density of states, which is the summing of all the states in your system, then you can see you've got a definite band gap in your whole system. Not just at some part in the Brillouin zone. Okay, what else? What else? Maybe one little bit of time just to look at graphene, which is a really sort of popular material to be studying, and it's a subject of Nobel Prize. Okay, graphene, you know what it looks like? It's just a single layer of carbon atoms in a hexagonal structure. It has a hexagonal unit cell with 2 atoms in the basis, one here and one here. So its reciprocal space will be hexagonal, and this shows you a sketch of the Brillouin zone corresponding to this lattice here. It's just 2-dimensional as well. These are very special and well-known points in your hexagonal Brillouin zone. You always have the gamma point, which is centered on your 0, 0, 0 K point. K is at the point here, and M is right in the middle of this line here. So for this kind of system, you have 4 electrons for each carbon atom, but what they do is they hybridize with each other and they form so-called sp2 orbitals so that it forms really strong and efficient bonds in the plane. And then there'll be 1 electron that has left out, and it forms a so-called pz orbital, which is perpendicular to the plane of your graphene. This is the corresponding band structure of graphene. Okay, you can see again it has this sort of characteristic free electron-like parabola at the bottom. It's got some very special bands up here, which give it many of its unique and desirable properties here. Okay, we'll talk about that next slide. But let's just look at it. We know it's got 4 electrons per atom. We know there's 2 atoms in the unit cell. We know that we have 8 electrons per cell then, 2 times 4. And we have 4 occupied bands. We have 3 of these type and 1 of these type. So that makes 4 bands. Each band can hold 2n electrons. So these 4 bands can occupy all of the electrons that are needed. 2, 4, 6, 8. Okay. But what you can see here is this is a so-called the Dirac point. So graphene is neither, these just touch you, so it's called a semi-metal. Okay. So we can look a little bit further and give names to these bands. As I said before, there's 3 kinds of these sp3 orbitals, so it can take 6 states. We have 2 atoms, so that means 12 states per cell. These form 6 sigma states. These are sigma states, 1, 2, 3. And there's also 6 sigma star states, which are up there in the conduction band. They are not shown. Okay? These pz orbitals, if you plotted them out in k-space, what they are like, we know that each p orbital can hold 2 electrons. So there's 2 states, spin up, spin down. And we have, therefore, 4 states per cell. Now, these states form what is called pi states. This is the pi band here, and then there is a pi star band, okay? Largely unoccupied. But what's the point? As I said before, this is the interesting part here. Remember we had this band structure, and if we're just zooming in at this point here, this pi band here is a bonding state, this is anti-bonding state, and if you look here, remember we could get the velocity by the derivative of the E versus K curve. Well, then we find that it has a very high group velocity of 10 to the 6 meters per second, because this is a very sharp angle here. And if you want to plot this out in sort of not just along this line here, but in 3D, it forms here a cone. This is called the Dirac cone here. So it has no band gap, but it also has no density of states at the Fermi level. So it's kind of an unusual material that I said, as before, it's called a semi-metal. Okay. Yeah, I think we'll